Hello, hello, check. Hello everyone, myself Harshit. I'm currently a master's student and I'm also tutoring side by side ever since my graduation. So this is just a demo video for the class 10th carbon compounds, but a little bit towards the end of the chapter. So we will be looking into the aromatic parts of the organic chemistry. So uh, this is a little more. This is a little more to the fact that you already know the basics and fundamentals, and uh, then what you get is a basic introduction to aromaticity. So make sure you do have a generalized idea about organic chemistry and its fundamentals. So yeah, the name of the chapter is of course carbon and its compounds. Now, there's one very interesting thing when we actually learn a little more about the organic chemistry. So, in the basic general organic chemistry, so far we have learned about the general nomenclature of the alkanes, haloalkanes, and again all the substituted members of organic chemistry and organic compounds. Now, there's one thing which we have also studied in particular was the nomenclature of cyclic alkanes and alkenes. Quickly revising what this is. So, for example, let's say we know that alkanes can exist in the open chain form structure. So this is an open chain structure, but it is also possible for me to draw a polygon with these shapes. So, for example, I can draw something like this, something like this, a pentagon, and also a hexagon, and so on and so forth. Now, likewise, we also saw that yes, alkanes can also, organic compounds, they can also exist in these cyclic forms, right? Broadly speaking, in organic chemistry, we call them as acyclic systems, the open chain compounds, and these are obviously called the cyclic systems as per their name. A quick recap about how do we do their nomenclature is again you start counting from the any lowest number. Depending upon the substituent attached or the functional group attached, the carbon atom is prioritized, and you can go either way finding the lowest locant. So if there are 3 carbon atoms, you use the word root as prop, right? And since it's an alkane, there are double bonds, so the prop plus ane, it becomes propane, right? But since this is a cyclic system, what we also do is we use a prefix cyclic before them. So cyclic plus propane, this gives us cyclopropane. One important thing to keep in mind here is just always keep the first letter capital and so on and so forth. So all of this is fine until we go to this particular member right here, which is cyclohexane. If I count it something like this, it gives me 6 carbon atoms, and yes, it's cyclic, so it gives me cyclohexane. Now, this is fine. Let's try to delve a little more down into this. Now, well, let's say what do I do is I take this cycloalkane again, and I'll just put this one double bond here. Now again, if we try to do the nomenclature of this, what we will get is 1, 2, 3, 4, 5, and 6. Alright. Now if I try to do the nomenclature, this will be what again? I will use a prefix as cyclo, hex, and on the first position I have a double bond 1-ene, cyclohexone. Similarly, I can put another double bond right here. So then what it becomes? Then it becomes cyclohex 1, 3 diene. Right? Now things change. You must be wondering, okay, that I can also put multiple double bonds here, right? That's not really possible. We will learn a little more later that why exactly I'm not putting a double bond between 2 and 3 carbon atoms. What ends up happening is this is not energetically favorable. Also, when we will learn a little more about ring strains and on. Now, if I try to put one more double bond here, ideally what you must be thinking is the name of this compound would become cyclohex, right? 1, 3, 5, and tri. right? This must be your generalized idea, but if you're thinking like this, okay, this is a wrong name. In fact, a compound with such name does not really exist in chemistry literature. What do I mean by this is, so we know these compounds are physical substances, right? Physical substances which we derive, we synthesize in lab. Now, this cyclohexa 135 triene does not exist in lab, as in there is no physical substance which is per this name of cyclohexa 135 triene. So, what exactly will be the name of this compound? So, now it brings us to this very new branch in organic chemistry, a sub branch in organic chemistry, which is called aromaticity. Aromaticity and aromatic compounds. Now, what do I generally mean by this? So, you must have studied in your class books and all. Generally, when organic chemistry was first not discovered, right? So, it was believed that, it was believed that the organic compounds can only be synthesized by nature and all until it was proven wrong. And similarly, there was one more of this assumption that there are two types of organic compounds majorly. So, first of them, one of them was aliphatic, and the next ones were called as aromatics. Now again, what's the difference between these two as per the name? Okay, you can see aliphatic, there is the word fat. So it was believed that these organic compounds can only be derived from the fats of animals, plants, and so on and so forth. Similarly, the word aromatic compounds, the class of these compounds, was given the name because they had this word aroma within them, because they had a very sweet, pleasant smell. Please keep in mind I'm using past had because yes, this definition has been discarded. Sweet, pleasant smell. So earlier it was believed so that okay, that's per the classification, but later on, as again the advancements grew, we learned more about organic chemistry. It was found out that okay, there are certain compounds in organic chemistry which are aromatic, but they don't necessarily have a pleasant smell. And in fact, this led to a very new definition of aromatics and aromaticity in chemistry altogether. Now we come back to our original molecule, which is cyclohexatriene. So there is no such molecule like this cyclohexatriene. So if you were to see this, okay, this is actually a very simplest aromatic compound. This is called as benzene. Now, what exactly is the difference between benzene and cyclohexatriene? Okay, so quickly going a little bit into this, okay, quickly going a little bit into the stereochemistry part of the chemistry. Quickly again describing stereochemistry is the study of science which deals with the configuration of the molecules, okay, as in how exactly our atoms are arranged in the 3D space. Now, one major difference between cyclohexatriene and all. So, okay, giving one more example of stereochemistry, you must have studied the tetrahedral structure of the carbon. So, on pen and paper, I can draw a carbon molecule with tetrahedral valency, something like this, which is a methane molecule CH4. But if I try to actually imagine the structure of this is not a linear structure. So, for example, if I imagine a sheet of paper and if I say, okay, the carbon atom is here and the four atoms are joined there, it's not a planar structure actually. The stereochemistry of the carbon atom is something like this, where in two of these hydrogens, they are in plane, and one of the hydrogens is protruding forwards, and one of the hydrogens is at the back. I think we have all must have studied this, right? So we all know very well that okay, that this is not a planar structure. In fact, these two bisect the plane of these two carbon atoms, and these angles are again 109.88 degrees. So similarly, there is just one major difference with this one stereochemical aspect. One of them is the planar structure of benzene. If I draw this molecule like this, okay, if I draw this molecule like this is a planar structure. meaning it will perfectly exist in a plane on a sheet of paper. There are no carbon atoms which are protruding forward. There are no bonds which are protruding or going inward. It's a very perfectly planar structure. Whereas we must have also studied that cyclohexane actually does not exist in this ring form, because we know due to the concept of ring strain, this is not at all feasible. This causes the bond to have a lot more repulsions with each other. As a result, the structure adapts. The structure changes to the most stable conformation of cyclohexane, which is its conformation. the the chair-boat conformations. So this is one of the most stable conformations of the cyclohexane. Now keep this in mind, okay, this structure is very much not planar at all. In this case, these atoms are going up into the axes, these are going down and then again up. Likewise, you have axial equatorial of hydrogen atoms which are protruding forward. So this is not at all a planar structure. Right? So this is one major difference. But again, coming back to the part as to how do we actually got to know about this, as to how did we got to know about whether this is cyclohexatriene or benzene in first place, there's something called heat of hydrogenation. So what you do is you take a molecule, okay, and let's say if I have to do addition of hydrogen in this, I have to do hydrogen addition. Now, when I have to do hydrogen addition, so obviously hydrogen will only be attaching itself to the place of carbon where there are more carbon atoms can be attached. So for example, there is this double bond, right? So this double bond can be destroyed and I can have one hydrogen attached here and one hydrogen attached here. And subsequently, this process will release energy. Yes, release energy, because breaking of bonds releases energy. Now, whatever that energy will be, okay, that energy can be measured with the help of a calorimeter. And when we did this experiment, it was found out that, when this first addition of hydrogen was done, there was some amount of energy released. Subsequently, if you try to add more hydrogen, okay, then there should be more energy, because obviously you're trying to destroy the stable structure of a molecule by adding something to it, so definitely there will be release energy. However, when there was a third hydrogen addition was done, this actually signified that there was a very big tremendous release in energy due to the stable conformation of the benzene molecule in itself. This again brought us to the attention that benzene in particular has very high stability. Now the question is, how does it have very high stability? Unlike cyclohexatriene, cyclohexane is not at all very stable. It can undergo reactions very quickly. Benzene can also undergo reactions, but they're not necessarily like the bond breaking ones. There are some other reactions which it can undergo. Now, what you must have seen probably in your books and textbooks is I can also draw benzene something like this. It's a little different question, but I can talk a little bit about it. It relates exactly to this question. So I'm going to draw three structures of benzene. One quick way to learn benzene is that you just have to draw a hexane and put alternating double bonds. Now, what have I drawn here? Let's see. If I name these carbon atoms again in any order, in this case it won't matter. So 1, 2, 3, 4, 5, 6, and again 1, 2, 3, 4, 5, 6, and again 1, 2, 3, 4, 5, and 6. So if you see carefully here, the double bond was between 1 and 2. Whereas in this structure, the double bond is between 2 and 3. And in this case, there is just a circular thing. Okay, let's talk about that a little later. Now this is where, like, we actually got to know a new concept which is called delocalization. Of negative charge. delocalization of negative charge, and we'll see what do I mean by this is. Let's try to understand this from an example. Let's say if I have to ask you your address or the address of your school, right? So there is one specific area which corresponds to the location of your school or your house, right? Not talking about the fact that if you have multiple houses, you have a hostel or something, a temporary home. But even with that, there's one particular designation, there's one particular address to which your house is located. You will say, okay, I have to go to XYZ street, take the left turn, and then opposite to this shop, I have my house, or so on and so forth. Meaning your house is localized, it's not changing its position over time, right? Similarly, the opposite of this localized is delocalized, something which changes position. So something which keeps changing its position. Now, what do I mean by this word here? Delocalization of negative charge, meaning movement of negative charge. So we know that negative charge is actually present in where? It's present in between these sigma bonds, and it's also present between these pi bonds. So sigma bonds are, we know, they are like perfectly stable, right? There is just direct orbital overlap, so the bond won't budge basically, right? But the electrons can still move, not in sigma bonds. But in pi bonds, the electrons can move. Since we already have studied this, that pi bonds, they are actually formed by the indirect overlap. So you have this space, this 3D space within which the electron can reside and also the electron can move. So electron is not bound to one specific position. That's exactly what ends up happening in benzene molecule. Let's see. So you again have these double bonds. So what ends up happening is, due to the planar structure of benzene, this double bond shifts from this, let's name the carbon atoms again. So 1, 2, 3, 4, 5, and 6. This shifts to the double bond between 2 and 3. And likewise, this carbon atom will now have greater valency, so this causes this bond to shift, and similarly causes this bond to shift. As a result, what you end up getting is a resonating structure, or this was also called as Kekulé structure based on the based upon the name of the guy who discovered this phenomenon. So this was found out to be that now this is the structure which we get in case double bond comes about between 2 and 3 in this their position. So you see how the negative charge within the molecule, and this keeps going on, okay? This doesn't stop anywhere. This keeps going on within the molecule like a circle. So we can see that the moment of this negative charge is like a circular motion within the molecule itself. As a result, the resultant of all these moments, I can show it something like this. I can draw a structure and I can put a circle inside it to show the circular moment of the negative charge. So yes, all these three, they are the structures of benzene. It's not that one of them is right. Okay, I hope you understood this. That will be all. Let's catch up in the next lecture.